at how to solve questions about finding the best or most optimal value using power of parabolas or quadratic relationships. Okay, so we're going to look at this question here. So Mr. Tang has 200 meters of fence, 200 meters of fence. And what else is going on? For each type of fence described, we want to determine the dimensions of the optimal fence. Optimal fence. So I like to highlight the question in a word problem in a different highlighter color. Determine the dimensions of the optimal fence. In other words, the fence that will produce the largest area. So we want to find some dimensions of a fence that will maximize the area. All right, so we're first going to look at the condition where Mr. Tang just builds a rectangular fence. Okay, so a good first step might be to draw a diagram. A nice labeled diagram. Okay. So I know it's a rectangle, and that's really all I know. So I'll draw a rectangle here. And if I want to label it, well, I guess I could label it with lengths, but I don't really know the length that's going to give me the largest area, though I may have a hypothesis. So I'm going to label this value x, some distance x. And I'm going to do the same over here for this side as well. Now, I could label this side y if I wanted to, but I think I could, if I'm crafty enough, define this side in terms of x somehow, so I don't need to introduce an extra variable. All right, so how are we going to do that? To do that, I might actually take a second to think of some examples. Some example rectangles that would satisfy this condition of having a total perimeter of 200 meters. So what might I do? Okay, I'll draw one like this. I'll choose a random length here. Say I'll choose 5 meters. That'll be 5 meters over here. And the question is, okay, well, if those are 5, how long must these sides be? Well, I know I've got 200 meters of fence to play with, so minus these two 5-meter sections, that would mean I'd have 190 meters left. And if I divided 190 meters by 2, 190 divided by 2, I get 95 meters. 95 meters. Okay, but I don't think I'm quite going to see this pattern unless maybe I construct a few other possible fences. And maybe then a pattern will begin to jump out at me. All right, so I'm going to choose another random side length here. And this time I'm going to make this side length 20 meters and 20 meters. And I'm going to see how this affects the length of this side up here. Okay, so to find the length of this side up top, well, I guess the first thing I'm going to do is I'm going to take away these two x's, these two 20 meters from my 200 meters of fence. So I'm going to take 200, I'm going to take away 20 and 20, so I'm going to take away 40, or 2 times 20. And then when I get that value, I'll divide it by 2, which gives me 80 meters. And 80 meters. Okay. You know, I might do one more just to make sure I really understand the relationship between the length of my sides. If I choose side lengths here, what does that make these side lengths here? So I'll do one more, and maybe I'll choose it to be something that I think might be a little odd. So I'll choose 35 meters. 35 meters. And again, to find out how long this side has to be, well, start by saying, well, I'm going to take away from 200 my 35s. So I can say subtract 2 35s. Okay, and that leaves me with 130 meters of fence for each of these sides. And I'll divide that by 2 to find out how much is going to be on top. This is 65, which is, looks like this diagram's not to scale, and 65 meters on the bottom as well. Okay, so some things might jump out at me if I look at some patterns. So like I might see a relationship that's consistent between the length and the width of these rectangles. It looks like they all add to 100. This is 5 and 95, that's 100. 20 and 80 is 100. 35 and 65 is 100. Okay, so if I want to know the length of this side here, I can say, well, that must be just 100. Take away the length of this side, which in this case is just x. Okay. Now, we would also be able to conclude that this side has the same length, 100, take away x, where x is some value of that length. Now, say you were a little confused about how to find this 100 minus x expression. What else could we do? Well, we could also retrace our steps and say, well, for instance, how did I find this value of 65? I could have said, well, I take away 200, and we took away 2 35s, right? We took away 2 times 35. Okay, so maybe if I generalize that step, I can say that's going to be 200 take away 2 times x. So maybe I'll write that down. The process for finding this side, this is x, that'll be 200 take away 2x. And then we got 130. However, we need to remember that that side wasn't 130. We then had to divide it by 2 when we were finished to get the number 65. So actually, the general process of finding this side length is we take this height here of 35 meters, and then we would say 200 take away twice that value, and we divide it by 2. So that is also another way we could represent this value. We could also say, if we wanted to, that is actually 200 take away 2x divided by 2, if we wanted. It's a little bit more cumbersome an expression to write in there, and so, but maybe it makes a little bit more intuitive sense to us. Either one is fine. And if you really want to get fancy, you will remember maybe from your grade 9 algebra operations that if I could rewrite this fraction as a 200 over 2, take away 2x over 2, which actually 200 over 2, well, that's just 100. And take away a 2x over 2, those guys cancel out, we get x. Okay, so I get 100 minus x after all. Okay, so that's step 1. I've got a labeled diagram. Labeled. Great. So now I'm going to move on to step 2, which I'm going to make an area equation. All right. So I know that the area of a rectangle is length times width, or if you prefer, length times height. Okay, so if that means the dimensions of this rectangle, this general rectangle, is going to be x times 100 minus x. 100 minus x. And that is something I can put into Desmos. I can take a look at that parabola. So step 3 is we're going to use Desmos. And we're going to get a sketch of what this thing looks like. Now I'm going to just draw the general idea here. We end up with a y-axis here and an x-axis here. We end up with a parabola that looks something like this. And there's a little vertex here. And that vertex is at 50 and 2500. We end up with a point here, which is at 100, 0. And we end up with a point here at 0, 0. Now, it's important to recognize that when we were measuring x, we defined x to be the length of one of the sides. This is we're measuring side lengths here. But on this axis, the y-axis, we were not measuring a side length, we were measuring an area. This is an area. So what that means is if we have an x and a y value, one of them represents a side length, but the other represents an area, and those pair together. So for example, the point 0, 0 means if your side length is 0 meters long, well, that would end up with a rectangle that would be 100 meters on each side, 100 meters, but 0 meters tall. And so that rectangle would have an area of 0. Alternatively, you could have side lengths that were 100 meters on either side, 100 meters, 100 meters, but have no fencing left for the rest of your side. So it'd be 0 in this direction, and again, you'd have an area of 0. However, the maximum possible area you could enclose is at the vertex. So for step 4 is we're going to look at the vertex. 50, 2500. And that's an x and that's a y, and that says that if you choose a side length, an x value of 50, if side length is 50 meters, you get a maximum area of 2,500 meters squared. All right. Maybe I could take that a little step further. We're asked for the dimensions, determine the dimensions of the optimal space. So I might actually go a step further, and I might just say, well, the length will be 50 meters, and the width will be, well, if my length is 50, that means I'll have a 50 and another 50 meters. And then how much am I going to have left? Well, it looks like I'm going to have 50 meters and 50. So my width is going to be 50 meters as well. And that's actually going to be my dimensions here. And that's our answer. Great. Okay. So moving on, maybe I'll put a little line here so I don't get confused. And we'll look at question B. Okay, so question B, again, we talk about a rectangular fence, rectangular. Still have 200 meters of fencing. And there's a key here. It has a barn wall that can be used for one side of the rectangle. So the implication here is we're building a rectangular fence against a barn wall, and a reasonable diagram might look something like this. So here's my barn, which I don't really care about. I care that it supplies a width here. So that's my barn, and this is my pen. And this is my fencing, and this is my pen in here, or area. Okay. Now again, I would have some 200 meters of fencing, which, if it isn't clear, only is really going to be making this side here, and this side here. I do not need to place fence along the barn. It's not necessary, because the wall of the barn represents I guess, one end of this enclosed area. Okay, so this is going to be a slightly different situation. Our process is going to be the same, but our specifics, our equation, our actual area equation is going to look a little different because the relationship between the length of one side and the length of another side is going to be different because we have different constraints. All right. So let's, okay, so what am I doing? So first thing, we start with a diagram, and that's kind of what I've begun here. So that's my diagram. Now, I haven't finished labeling it yet. So I guess the first thing, again, is to decide on a variable. I'll decide again to let this side be my variable x. And that means this side is also x because it must have the same length here. And the question is, well, what value of that x, and therefore what value of this width, will give us the maximum area in this case? Now, in order to find the length here, I could call it y again. I would introduce another variable in doing so, so I'm going to try to somehow define this side length in terms of x. And again, kind of like I did in the first question, it might help us to maybe brainstorm some examples. So I'm going to write down some example situations where we can use 200 meters of fencing in this constraint. So, okay, so let's write out some examples. And change this over here so we can see what I'm writing. All right, so an example may be, well, that I could maybe make a fence that looks like this. And has a side length here of, let's say, 30 meters. And that means this one would be 30 meters. The question is, how long would this side need to be? Now, I would invite you to pause the video for a second and think about your answer before continuing to watch. Now, if I say I have 200 meters of fencing, I'd take away 30 and another 30. That actually leaves me with 140 meters of fencing left. So what did I do to find out that 140? Well, I said I got 200. I'd take away 2 times 30, which was 140. And in this case, I don't need to divide it by 2 because I'm not splitting the leftover length between this side and this side. Another example, okay, I can pick any number really. Let's say 41 meters. And so it's going to be a little bit different shape, 41 meters. And I'll have some distance here. And if I would pretty much do the same operation. I would say 200. I'd take away 2 times 41. Oops. 41, delete. And that gives me, 2 divided by 2 minus 200, take away 2 times 41. Let's try that one more time. And I end up with 118 meters left over. So what did we do in this process to find the length of this side? Looks like every time we just took 200 and we took away 2 times the length of that side. And the length of this side is just x. So to find the length of this side is just 200, take away 2x. Okay, that's a good first step. The next step is we want to write out an area equation. Area equation. All right, well, area is length times width. And again, we're going to say we're going to get the area, which is going to have a length x of general area. We're going to multiply that by the length along here, which is 200, take away 2x. Okay. And that gets us started. That's something we can throw into Desmos. So step 3 is we're going to put that into Desmos. And if we do that, we end up with a graph of a parabola, and depending on how you define your window, it could look something like this. And at some points, we have a point here, a point here, and a point here, and we end up with a point at 0, 0. We end up with a point at 0, 100. And we end up with a point here, halfway through the middle, that the coordinate of that vertex is the point 50. And, wait, hang on a second, 50, that must be 5,000. Sorry, I'm not looking directly at Desmos right now. Okay, great. And maybe we take a second to reflect, what are we measuring along x? We're measuring a side length. That's this guy, x. And what we're measuring in y, we're measuring area. How much enclosed space there is. Okay, and so if I look at, say, some points here, I say, well, it's point 0, 0. That means if I choose my side length x to be 0, y enclosed 0 area. Oops, that's not right. That's the other way around. 100, 0, pardon me. If I choose my side length to be 100, each of these guys are 100, how much space do I have left for this side? 100 there and 100 there, that's 200. That's all the fencing I have left, which means I would have 0 fencing for this side here. And again, that would enclose 0 area. Pardon me. However, if I look at this value of x and this value of A, we're going to find we have enclosed a maximum possible area of all these potential side lengths. And so we're going to look at our vertex here. That's the point 50, 5,000. And so what does this say? This says if we choose a 50-meter side length, or length of one side, we'll maximize or optimize the area to be 5,000 square meters. In other words, the length would be 50 meters. But what would the width be in this case? Well, if I use 50 meters on this end of fencing, and I use 50 meters on this end of fencing, how much do I have left for this section? Well, I must have 50, 50, 100. I must have 100 meters left. 200, take away 50, take away 50. And those are the dimensions of my pen. All right. Moving on. All right, we have, now that we're starting to get the process here, we're going to maybe speed this up a little bit. So we're looking at, again, we have a rectangular fencing situation. And we have 200 meters written on the other side of the page. I'm going to write it down here as well. 200 meters fence, so I don't forget that still applies to this question. And it's partitioned into 2 equal rectangles. Okay, so it's a rectangle split into 2 equal rectangles. All right, I'd take a second before continuing watching this video to try to draw a sketch of what you think that statement means. Okay. So what this means is we would have a rectangle like this, and we would split it into half. We'd split it in 2 with maybe another piece of fence, and maybe that line of fence goes down here like that, but actually it could also have gone across like so. So maybe I drew the same rectangle, and I've drawn it like so. Okay, these are really identical as far as mathematics is concerned. So let's start with step 1, which is we're going to have a labeled diagram. That is not how you spell diagram. Diagram. Okay. And I'm just going to choose one of these 2 models at random. All right, and I'm going to split it in two. It's going to have another piece of fence going through the middle. And that is roughly equal. Okay, now I ended up defining these sides to be x, and x, and x. And really, I need to decide what the length here should be. I don't actually know what that number should be. Legitimately, I don't know what it should be. I'm going to play with it a little bit myself. So you guys get to see how I would go about solving something like this. I would start by playing around with the numbers. So I might choose a random value for x, like 20. 20 is a nice round number. And say, okay, well, I had 20 there and 20 there. Oh, right. And draw the rest of the diagram so you can see what I'm labeling. And 20 meters. Okay, how much must this side be? So I would probably add all those up. That's 20, 20, 20. Okay, so that is 60 used up already. So I think you can already do that in your head and say that's probably 140 meters, but just to clarify what I'm doing, I'm saying 200 take away 3 times 20, right? And that leaves me with 140 meters. However, how many fences do I have left? I have 2 equal sides. So I have to divide that value by 2. And that gives me 70. Okay, so I'm starting to feel like I can see what the pattern is, how I'm going to get this side given these ones, and also seeing some other examples we've done before. I think I have an idea, but I'm going to test it now. I'm going to test it by trying to make another rectangle that satisfies its conditions. All right, so they've got to be the same. So maybe I'll make this one 40 this time, 40 meters, 40 meters, and 40 meters. To find how much fencing I have left, I would obviously take away from 200. I'd take away 3 40s. Leaves me with 80. Oh, this is going to be unexpected, okay. And that means I have 80 meters left for both, so I'm going to divide that by 2, and I would say that, okay, that means I have 40 meters for this guy as well. Obviously, this diagram was not drawn to scale, but I didn't know that until I began. Okay. So what's this process I've been doing? I'm just going to try and retrace my steps. Seems like, okay, I divide by 2, and can I go any further back? Oh, I can't, okay. Oh, wonderful. All right, so it seems like what I'm doing to get this side length is I'm taking 200, and I'm taking away 3 times the length of this side. Take away 3 times whatever that side length is. So in this case, it's 40. And then it seems like I've been dividing by 2. If I want to keep that all in a calculator, I might just put brackets around that. Okay, insert 200. And then I divide it all by 2. Okay. Oops, 2 and... Oops, okay. So there's the whole idea. 200 take away 3 times my side length and divide it by 2. And equals 40. Right, okay, so that is what I did. Now, in our general case, our side length is x. So instead of saying 200 take away 3 times 40 divided by 2, I'm going to say 200 take away 3 times x, my unknown, and then I'll have to divide in half. So I have some for this side and some for this side. So I'm going to just write out that as a general statement. 200 take away 3x, and I might put that in brackets and divide the whole thing by 2. Now, alternatively, you might prefer to think of it as 200 take away 3x over 2. Divided by 2 and over 2. Those are just 2 ways of expressing the same idea. Now, what's interesting here is that this actually doesn't simplify nicely. I mean, it simplifies a little bit. If we compare how we approach question A, I could say, well, this is 200 over 2 minus 3x over 2, or 100 take away 3 over 2x. Okay, so I mean, maybe you want that instead. I don't know. I kind of like this one. It helps me to retain all the steps we're doing. This will be a little easier to type into Desmos though. So I guess you'll have to pick your poison. Okay. So the next thing we'll do is we'll start with an area equation that we're going to maximize. All right, and obviously it's area is length times width again, so we're going to have a length of x and a width of 200 minus 3x times 2. So our area is either, maybe you'd like to say it's x times 200 minus 3x all divided by 2. Or if you prefer, maybe you like this one, maybe you want to say area is 100 take away 3 over 2x, that's this length, times x. Of course, you can put the x in the front, actually it doesn't really matter. Okay, cool. And then we're going to put that into Desmos and take a look at it. Okay, I'm going to need to take a second to do that myself. Sorry. Alright, so area equals x times 100, take away 2, 2, x, and I'll have to zoom out, just like we have been on the other ones. Alright, and we are going to end up with a parabola shape. It looks like it's got some unique points here. Interesting. Alright, so we're getting a parabola, 3, and that's Desmos. We're going to move on, to our Desmos step. Thank you for being patient there while I looked up exactly what this graph looked like on Desmos. Wow, that vertex is way up there. So great. And I end up with a vertex. Okay. So I end up with a y and an x. And I get a vertex up here, and it's at a value of, oh, it looks like a decimal, 33.3 repeating, and 1,600, and I'm just going to round that to 67. Actually, I didn't round that one, so maybe I'll keep this. 66 point, or rather 6, Okay. And I think it's interesting to also note the values of the x-intercepts, which is 0, 0, and 66.7, or 66.6, and 0. Great. Now, of course, we're talking about on x our side lengths. So x is our side lengths. And y is measuring area, just like the other situations. Okay, and so then we're going to move on, and we will inspect and think about our vertex here. And our vertex, well, that's the point. I'm going to round that to 33.3 and 1,667. There's an x and a y, which remember we measure area with our y. It's an area. Okay, so maybe we can make that into a statement. We can say, well, if our side length is 33.3 meters, we maximize our area to be 1,667 meters squared. Okay. And then the dimensions of this fence would be, I guess it would be 33.3 meters in this direction, 3 times, And how much would I have left for these guys? Well, I might take a second to think about that. What is that dimension of this side of the rectangle? It'd be 33.3 times, nope. So it could be 200, take away 3 times 33.3. Then I have to divide that by 2. And I end up with a distance of 50 meters. Now, because I rounded 33.3 repeating to 33.3, I get this little artifact. But actually, this would be 50 meters on either direction. That means the length would be 33.3 meters, and the width would be 50 meters, which is a little counterintuitive to me. I don't think I would have assumed those dimensions. I'll draw a little line here, like so. Okay. So, moving on, we'll look at our last question. Rectangular fence is partitioned into 3 equal and parallel rectangles. Well, that's not so different than our last question, which is a rectangular fence, which is partitioned into into 2 equal triangles, rectangles. Now it turned out they were both parallel to the lines that separated those rectangles were in parallel with each other. Now we're going to see why this is a little bit more important in this case to draw attention to. All right, before you proceed, I would recommend you take a second to maybe grab a whiteboard or a piece of scrap paper and try to draw what you think this diagram is going to look like. Okay, so I'm going to start with a diagram of a rectangular fence, a rectangular enclosure. All right, something like this. And then I'm going to partition or split it into 3 equal parts. And the parts are all going to be rectangles. So they're going to be equal rectangles. It's going to look something like this, like a tricolor flag. Okay. And of course we label up our diagram, so it's X. This will be X as well, X and X. And again, we encounter this familiar question of, well, what do we label these long sides? Okay. You may have noticed a pattern by now, and if you feel like you have, you're welcome to continue it. However, I think I have a pattern, but I'm not quite sure, so what I'm going to do is I'm going to write out a few examples. All right, so I'm going to choose a random side length. Maybe something easy for me to think about is 25 meters. And 25 meters, 25 meters, 25 meters. I chose that because I know those add up to 100 in the same way that 4 quarters add up to $1. That means I have 100 meters left. But just to confirm that, I would say I would take 200 and I would take away those 4 times 25. And again, I would divide all that by 2. So I'll equal and divide by 2, and that leaves me with 50 on this side and 50 meters on this side. Okay, I think I'm seeing the pattern here. All right, so it looks like what I'll do, pretty similar to last time. This side must be 400, 200, take away 4 x's, and we're going to divide all that by 2. Okay, and also as an aside, I'm going to ask, can I simplify that? And it looks like I can. 200 over 2, take away 4x over 2. That's going to simplify. 200 divided by 2 is 100, and it's 4x over 2. That looks like I'll take 100, take away 2 times x. Okay, and so I could also label that 100, take away 2x. All right, my next step is an area equation. So as before, I'm going to multiply the length times the width. As my area is going to be x. times 100 take away 2x. All right. Now, move on, and I'm going to put that into Desmos. I'm going to draw a little sketch here. You don't have to draw a sketch, but I just want to show you what I'm looking at. Okay, so we end up with some points here, 0, 0, and a point here at, I guess that'd be 50, 0. And this guy here would be at, pardon me, 25. And 25 times 100, take away 50. 25, take that's going to be 50. 25 times 5 is 1. 2, 5, 0, I think. I'm just going to confirm that. I'm going to choose 25 times 100. Take away 2 times 25. Sorry, I'm not looking at Desmos right now. 1250. Okay, great. All right. So we've learned, I think, already we're measuring side lengths here. And we're measuring an area here. So lastly, we're going to look at the vertex, point 25, 1250, 25, 1250. Okay, and that's an x, that's an area, so that means we're going to have an, oh, by some coincidence, I realized actually I had selected in my first random thought the area that will represent a maximum. I've already done that because when my x is 25 meters, we maximize or optimize the area to be 1,250 square meters. Great, and the dimensions of my rectangle, I've actually got a diagram right here. My length is 25 meters, and my width, the amount I've left, would be 50 meters. And those are the dimensions that will maximize the area of this fence.